Welcome to this explainer. Today, we're diving straight into something absolutely massive, the incredible cyber-physical convergence that's happening all around us. We are officially moving way past the old days of just crossing our fingers with reactive, guess-and-check decision-making. Instead, we're entering this wild new era where our physical reality is seamlessly synced up with highly intelligent virtual replicas. So, think about this for a second. What if you could actually predict the future of a physical object before anything even happens to it? I know, it sounds totally like science fiction, right? But giving teams the ultimate predictive power to safely test out thousands of scenarios in a digital environment, that is happening right now. By prioritizing prediction before taking any real-world action, organizations are drastically slashing the risks, the costs, and even the environmental impact of physical interventions. It's a total game changer. Now, to really wrap our heads around how we got here, we've got to look back at its aerospace roots. As aerospace engineer Dr. Karen Wilcox puts it, a digital twin is a personalized, dynamically evolving model of a physical system. And the foundation for this life-saving concept actually goes all the way back to 1970, during the Apollo 13 rescue mission. When that oxygen tank exploded out in space, NASA Mission Control didn't just guess what to do. They used high-fidelity simulators down on Earth to troubleshoot the anomaly and test survival strategies in real time. They literally used a remote replica to save the physical ship and its crew. Incredible, right?
Okay, let's look at our roadmap for today. We're going to cover beyond simple simulations, the anatomy of a twin, how this is transforming our physical world, the fascinating biological digital twin, and finally, ethics and the future.
Let's jump right into Section 1, Beyond Simple Simulations, and shatter a few myths. First things first, we need to clear something up because it's a super common misconception. A digital twin is definitely not just your standard computer simulation. You see, a simulation is typically used early on, during the design phase, just to answer theoretical questions. It's static, but a digital twin, it is a persistent, living, breathing entity. It evolves right alongside one unique, specific physical asset. So while you might simulate a generic wind turbine design, a digital twin is mirroring your exact turbine. Let's call it serial number 882. It tracks that specific turbine's real-time wind exposure, its vibration, and its entire repair history. And the really crucial part is that it's bidirectional. That means the insights gathered in the digital world actually flow right back to influence the physical object itself. When we trace this history, it's pretty amazing to see the leap from those disconnected Apollo simulators to today's fully autonomous cognitive systems powered by AI. After Apollo 13, the concept took a massive leap in 2002 when Dr. Michael Greaves formalized the framework linking physical and virtual assets. Then, jump to 2010, NASA engineer John Vickers officially coined the term digital twin. And here we are today, witnessing the integration of agentic AI. This is where large language models empower these twins to not just mirror reality, but to actually reason about it and execute management strategies completely on their own. Moving on to Section 2, the anatomy of a twin and the digital thread. Let's look under the hood for a minute. How do we actually build this digital thread connecting the physical and virtual worlds? Well, it's done by combining massive, and I mean massive, IoT data streams with heavy computing power and physics-based machine learning. At the absolute base level, you've got a super dense layer of IoT sensors feeding data. We're talking vibration, thermal, LiDAR, the works. Then high-performance computing, like NVIDIA RTX GPUs, processes all that heavy throughput. But the real secret sauce? That's physics-informed neural networks, or PINs. These networks bake the fundamental laws of physics directly into the machine learning pipeline. So even if the sensor data gets noisy, the AI's predictions will never violate the basic rules of nature. So this whole technology builds through a four-stage lifecycle of AI integration, ultimately culminating in intelligent agents that can reason and fix problems totally autonomously. It kicks off with modeling the physical foundations. Then it moves into mirroring the real-time state using generative AI. After that, it steps up to forecasting and intervention. And finally, the holy grail, autonomous management. By the time we hit this fourth stage, the system isn't just flagging an operator saying, hey, there's a problem. No, it's actively recommending the exact optimal fix, adapting to curveballs on the fly. Okay, Section 3, transforming our physical world, going from the micro to the macro. Let's take a little tour of scale, zooming all the way out from microscopic parts to massive global systems. At the most granular micro level, we have what's called a component twin. This focuses purely on the real-time stresses and dynamics of just one single piece of hardware. Imagine an offshore wind turbine blade. A component twin continuously absorbs real-time strain gauge data, mixes it with local weather forecasts, and instantly optimizes the pitch of that one specific blade. This maximizes energy yield while completely protecting the physical structure.
Now, when you take all those individual components and synchronize them together, they form a complete interactive asset twin. Take a massive manufacturing plant, for example. An asset twin gives you this fully immersive 3D view of an entire bottling line. You could instantly see that, say, filler machine number 1 has a conveyor jam. You zoom right into the exact component and get a customized AI-generated recommendation on exactly how to fix it, all without ever having to walk across the actual factory floor.
Let's zoom out even further. Urban planners are now using system twins to process literally billions of inputs, which is cutting AI development times in half for major issues like traffic congestion in Paris. By piping millions of live camera streams right into a system twin, developers can test out smart traffic signals and brand new routing protocols on a virtual citywide scale. They can deploy solutions that drastically reduce travel times and emissions, and they do it without tearing up a single physical road. Finally, at the absolute macro level, we have process twins. Companies like DHL and Maersk are basically using these as a crystal ball to stress test their entire global supply chains against wildcards like port strikes or natural disasters. Organizations can simulate, for instance, exactly how a labor shortage at a distribution center in Brazil is going to impact delivery times worldwide. This gives them the power to proactively reroute inventory and keep their delivery promises, no matter what happens. Check out this number, 76%. That is a truly staggering reduction in herbicide application achieved by John Deere. And how did they do it? Agricultural digital twins, optimizing precision farming. By blending computer vision with software-defined farming models, these tractors can target individual weeds with absolute pinpoint accuracy. It's a huge win, protecting the environment while dramatically boosting the farmer's yield. Or how about $1.7 million? That's the massive amount of money a team saved on rework for just one single office building. They did it by virtually eliminating errors before a single drop of concrete was even poured. In construction, rework can normally eat up to 12% of a project's total budget. But by simulating the entire build in a digital twin, they identify clashes, like plumbing running right through an HVAC duct, long before the physical materials ever arrive on the job site. Just look at the stats here, like that 30 to 50% drop in troubleshooting time. Leveraging agentic AI and immersive 3D isn't just about making things look cool, it is about delivering monumental returns on investment and ensuring operational longevity. Thanks to predictive maintenance, we're also seeing a 40% reduction in wasted parts inventory. By shifting away from that old reactive fix-it-when-it-breaks mindset to a highly predictive model, these twins are adding years to the lifespans of incredibly expensive industrial assets. All right, moving into section 4, the biological digital twin, where we are literally replicating life. Because you see, this tech isn't just for heavy machinery anymore. By continuously assimilating personal data, we are pivoting to the ultimate complex system, human biology, and our own personal lives. We're shifting from broad, population-based models to ultra-personalized precision care. Right now, cardiologists are creating digital replicas of individual patients' hearts so they can fine-tune pacemaker settings before they even operate. For devastating diseases like ALS, digital twins can actually forecast when a patient might need a wheelchair months in advance. They're even being used to supplement placebo groups in clinical trials to get life-saving treatments to market much faster. And honestly, it gets even more personal. On the professional side, you can now feed your resume, your communication style, and personality tests right into an LLM to build a career twin. It'll practice tough interview questions with you and specifically target your weak spots. And that brings us to our final section, Section 5, Ethics in the Future of the Industrial Metaverse. As we look to the horizon, making this huge leap to fully autonomous, synchronized environments brings up some pretty profound questions that we're going to have to navigate as a society. We have to carefully untangle things like data ownership and strict privacy regulations like GDPR. For instance, who really owns your medical digital clone once it's been fed into a corporate AI system? And if an algorithmic twin is basing decisions on historical data that might be biased or flawed, how do we make absolutely sure its choices are fair and transparent to everybody? Plus, just on the pure technical side, to support these massive real-time virtual ecosystems, we're going to absolutely need the sub-millisecond latency that only the upcoming 6G networks will be able to provide. When you look at the projected market growth, it is completely explosive. This perfectly illustrates what happens when these technologies graduate from isolated niche applications into a massive, shared, immersive world. We are looking at a leap from $28 billion in 2024 to over $228 billion by 2029. We are standing at the dawn of the industrial metaverse. This is a space where entire global systems interact seamlessly and where agentic AI evolves from simply mirroring our physical world into creatively collaborating with us to solve complex problems. So I'm going to leave you with a provocative thought to ponder as we wrap up today's explainer, especially as we prepare to inhabit a future where almost every part of our physical reality has a thinking digital shadow. As our physical and digital realities fully converge, how will we redefine human-machine coexistence in the industrial metaverse? Seriously, think about that the next time you look at a skyscraper, a commercial jet, or even just check your own fitness tracker. Thank you so much for joining me on this deep dive, and I highly encourage you to keep questioning what's possible as we build the world of tomorrow.